Okay, in the last lecture we introduced at the end the concept of activity, and that's defined as follows: that the chemical potential of I is equal to the chemical potential of I in its standard state plus RT ln the activity of I. And we showed how, for some simple cases, the activity of I was related to the composition, the mole fraction of I in the mineral. And I gave you a couple of solid reactions to look at. One was this one. In which the fayalite plus quartz reaction that we've looked at several times already. Which break down at high pressure to form orthopyroxene ferrosilicate. And we know that at equilibrium, the chemical potentials of the products minus those of the reactant, mu of Fe2SO4 minus mu of SiO2 equals 0. And then if we substitute mu 0 plus RT ln A, for each of those, so products minus mu 0 Fe2SO4 minus RT ln activity of Fe2SO4 in fayalite minus mu 0 SiO2 minus RT ln activity of SiO2 in quartz. Then if we collect the chemical potential, the standard state values on one side and the activities on the other, and we use relationships like x ln y equals ln y to the x and ln y minus ln x equals ln y over x. Remember those. Then we find that collecting mu zeros on one side, 2 mu 0 FeSiO3 minus mu 0 Fe2SO4 minus mu 0 SiO2, and the activity terms on the other side is minus R times T times the log of the product's activity of FeSiO3 in ferrosilicate squared, because there are two, we use this relationship, divided by the activity of Fe2SiO4 in fayalite times the activity of SiO2 in quartz. This lot is called delta G0, the standard state, the change of free energy in its, for every component in its standard state. And this is usually called the equilibrium constant K. And then we we showed that for a solid solution, the activity of, if we take an FeMg olivine, for example, then if we use the standard state of the pure phase at the pressure and temperature of interest, then fairly obviously, if our phase is pure, and our standard state refers to the pure phase at the pressure and temperature of interest, then mu equals mu0, and activity is 1. So if our standard state is the pure phase at the pressure and temperature of interest, then activity of Fe2SO4 equals 1 if it's pure. Otherwise, the activity of Fe2SO4 is equal to XFe squared. And this 2 comes from the fact, as I showed, that there are 2 moles of iron and magnesium in the formula unit. So you get double the amount of entropy, 2 Avogadro's number of sites. Okay? And again, fairly obviously, when X is 1, it's pure fayalite, and A equals 1, as I said there. So, if we look at the equilibrium constant, so if you're doing this kind of problem, you set for the pure, if all the phases are pure, delta G0 is going to equal to RTLM1. Which is 0. And so if we look at K, is activity of SiO3 squared over the activity of Fe2SiO4 times the activity of SiO2. And the activity of FeSiO3, only 1 iron and magnesium atom if it's an FeMg SiO3 solid solution. There's only 1 in the formula unit, so it's simply equal to X. And in this case, the activity is X squared. So here we have X all squared, and here we have X squared. So K then is equal to XFe in the pyroxene squared divided by XFe in the olivine squared. And assuming the quartz is pure, it very rarely has anything other than pure SO2 in it. The activity of SO2 is 1. Alright? In the other question I gave you, it was a bit trickier because there was a lot more iron and magnesium mixing. So for this reaction, that's the cordierite. Goes to garnet. Plus 4 silimonite. plus I think it's 1 SO2. So it's garnet, limonite and quartz. And if we have FeMg mixing, then the activity of this component in the cordierite is equal to XFe squared and the activity of this component in the garnet equals XFe, and there are 3 in the formula again, so cubed, where XFe is obviously the ratio of iron to iron plus magnesium. Now, when we look at the equilibrium constant for this reaction, K is going to be equal to the activity of Fe3AO2SI3O12 squared, because there are 2 moles, times the activity of AO2SiO5 to the power 4 times the activity of SiO2, all divided by the activity of Fe2Al4 Si5O18 squared. Sorry, cubed, because there are 3 here. Now, if we assume all activities are 1 except for the garnet and the cordierite, K then becomes equal to, this is XFe and the garnet cubed, the activity, and it's all squared, so it's x to the 6th. We assume that's 1, pure Al2SO5, pure SiO2, and this is XFe and the cordierite squared is the activity, but it's XFe squared all cubed, so it's also XFe to the 6th. Okay? Every year I ask a similar question. Every year somebody gets the powers wrong, but if you want to know, you should have the same power because you've got the same number of atoms of iron on both sides. And so you'll end up with the same power. So in this case, I think the equilibrium constant in the second part of the question was 2 to the power 6. Which is 64. So it was 0.8 to the 6th over 0.4 to the 6th is 64. Now that's using the standard state of the pure phase at the pressure and temperature of interest. Okay, why does that matter? Why do we need a standard state? Well, we need to know, because none of these chemical potentials and free energies are absolute values, because they're not absolute values, they're all relative values, so we need to know relative to what, okay? And so we're looking at them relative to the pure phase, and our mu0 is actually also normally relative to the pure elements at the pressure and temperature of interest. So there's a lot of relativity involved. But we need to know, because it's very, very easy to make a mistake if you don't know what your standard state is. And actually, I've been reviewing a paper, a manuscript this week, in which it's written mostly by a student, but also by a senior academic, in which they don't know what their standard states are. They've completely messed it up. And it's crazy, because it's elementary. Anyway, let me give you an example. Whatever your standard states are, doesn't change the answer. That's the important thing. It won't change the answer, but it will change activity. And I'll give you a nice simple example now. Let's take a reaction involving a gas that we've talked about already. So you know how to calculate this reaction. It's the reaction between calcium carbonate and SO2. Impure limestones often have quartz in them, sand grains, and at high temperatures they react to form this mineral, which is not a pyroxene. It's actually, it looks like a pyroxene in terms of its formula, but it isn't. Oh, that's strange. So this is calcite. That's wollastonite. What's kind of weird in thin section is it's got several cleavages that intersect at strange angles. Plus gas, CO2. And we showed, we talked about the equation of state of CO2 and calculated the fugacity of CO2. Let's consider a couple of possible standard states for CO2. Okay. Let's suppose that we know the free energy at some temperature, let's say 298. Okay? So that might be room temperature, 298. And as we go up temperature, the free energy goes down because it's minus T times the entropy. So as T goes up, the free energy or chemical potential of pure CO2 will go down. Until we get to here, so this is at 1 bar. So this will be the free energy at 1 bar and some temperature T. And then we compress it. We take the free energy up. And that is the integral of VdP. Okay? So this is the free energy at 1 bar and T, that's the free energy at P bars and T of pure CO2. Okay, let's suppose that we use a standard state of P bars and T and all phases are pure. Okay, so Standard states, all phases pure phase at P and T. Okay, so delta G0 then is going to equal delta H0 minus T delta S0 at T plus the integral from 1 to P, the volume of CO2 dP plus P minus 1 into delta V solids. We did this before. Okay, so here is the pressure volume term. So we go up temperature and then we go up pressure. And the PV term for the solids, of course, is very simple. For the gas, it's more complex. We need the equation of state for the gas to do that. And that equals minus RT ln activity of CO2 times the activity of CaSO3 in molastonite divided by the activity of CaCO3 times the activity of SiO2 in quarts. So all phases are pure. If all phases are pure, all activity equals 1 because everything is in its standard state at the pressure and temperature of interest. Now suppose that instead of standard state at P bars and T, we do that for the solids, but for the gas, we put the standard state here at 1 bar and T. So let's let standard state of CO2 be pure CO2 at 1 bar and T. So what happens now? So delta G0 is equal to delta H0 1 bar and T minus T delta S0 1 bar and T plus P minus 1 into delta V solids. But this term disappears from delta G0 because it's no longer our standard state. Our standard state is at 1 bar and T. So for CO2, mu equals mu 0 plus RT ln A and this refers to 1 bar and T, and this is at P bars and T. And so obviously these are no longer the same, but the difference between them is that integral. Okay, here's now our mu 0 and there's our mu. So it's just that. So RT ln A is the integral from 1 to p of v dp. Okay, so it's no longer activity 1. It's activity, or RT-LMA is the integral of v dp. Now, in this case now, all of these are 1 because our standard states are all pure phase at P and T, and all our phases are pure. So in this case, delta H0 minus T delta S0 plus P minus 1 delta V0 solids plus the integral from 1 to P of VCO2 dP equals 0. Now RT ln A CO2 is the integral of V dP. So this is case 1. Case 2, delta H0 minus T delta S0 plus P minus 1 delta V0 solids. So if all phases are pure, that's our delta G0. And that equals minus RT ln activity. Okay, better rub that out. So all phases are pure, so these are all 1. That's 1. But RT ln A CO2, just rubbed it out of course, is integral of VDP. So that is now equal to minus the integral of VCO2 dP. Okay, so these are all 1, so it's RT ln A CO2 minus, so minus the integral from 1 to P of VCO2 dP. So all we've done, in this case, everything is pure and all standard states are at the pressure and temperature of interest. And so we set that to 0, where K is 1. And in this case, we took our standard state for CO2 to be there, which is something we very often do with gases. And in that case, the activity RT ln A is equal to the integral from 1 to P of VDP, VCO2 dP. So now, this term goes on the other side of the equation. Right? So instead of being 0, it's that. But it's the same. Exactly the same answer. So it doesn't change. Changing it down to... Alright, so we have these two answers which are the same answer. So for our standard states as a pure phase, case 1, we have delta H0 at 1 bar and T minus T delta S0 plus P minus 1 into delta V0 solids we separated we separated the volume of the gas from the volume of the solids, plus the integral from 1 to p VCO2 dP, and that's 0 if all phases are pure. And then we said, using case 2, where CO2 standard state is the pure CO2 at 1 bar of the temperature of interest, we have deltas H0 minus T delta S0 plus P minus 1 into delta V0 solids equals minus integral from 1 to P of VCO2 dP, where this is now the RT ln activity of CO2 relative to its 1 bar standard state. Okay, so we showed that the integral from 1 to P of VdP for a perfect gas that's equal to RT ln P. Right? We substituted the perfect gas law, PV equals RT, and integrated to get that. So, in case 2, this is RT ln A. So RT ln A CO2 with a 1 bar standard state equals the integral from 1 to P of VdP equals RT ln P. So if we use a 1 bar so with standard state of pure gas at 1 bar and T, A equals P if it's a perfect gas. So that's well, a nice, easy result. And that's one reason why we often use this 1 bar and T standard state for gases, because it gives us a nice, simple relationship to pressure if it's a perfect gas. And if it's not perfect, we introduced a fugacity coefficient. And if CO2 isn't pure in the mixed case in nature, which it often isn't, then the activity of CO2 will equal P times capital gamma times X, where X is the mole fraction, X CO2. Obviously, gases have entropy of mixing the same as everybody else, as everything else. So X CO2 is moles of CO2 over H2O plus CO2 plus whatever else you've got. So Typically you might have some methane or hydrogen and so on and so forth on a molar basis. Okay, so for a perfect gas, if we use a 1 bar T standard state, A equals P. Similarly, as we showed last week, that is going to equal RT-LMP as well if we use the standard state of the pure phase at the pressure and temperature of interest. Anyway, that's what happens when we change standard states. We put various terms in free energy over into activity. All right? Now, a thing that I realised I didn't explain in more detail is if we take a solid mixture, like olivine we've talked about garnet, we've talked about cordierite, but we've only talked about iron magnesium solid solutions. We haven't talked about anything more complicated than that. However, the result which I gave you applies no matter how many components you have. All right. So we could take, for example, a garnet would typically, one of my favourite minerals, garnet. Garnet would typically have calcium, magnesium, iron, manganese, all replacing one another, substituting for one another. So in that case, if we took the component Ca3Al2Si3O12, then its activity should equal XCa to the power 3, where XCa is equal to Ca over Ca plus Mg plus Fe plus Mn. Okay, so I only talked in detail about iron magnesium solid solutions, but you can show, and of course you do have to do the differentiation 4 times instead of once, if you didn't want to do this, no, 3 times. But you can show that that result applies no matter how many components you've got, which is quite nice. Well, it's very nice. It makes life very easy in principle. Now, what do we do? I mean, this is what's known as an ideal solution, in as much as the only contribution to the free energy are the free energies of the end members and the entropy of mixing. All right. So, but non-ideal solutions are quite common. So, for example, iron and magnesium solid solutions, they're really close to ideal. So this is a very good assumption. But for garnet, calcium and magnesium don't mix ideally at all. They mix quite non-ideally. The reason being they're very different in size. Calcium is a heck of a lot bigger than magnesium. So then we need to introduce activity coefficients in the same way as we introduced fugacity coefficients. So the activity x Ca cubed times some coefficient call it the activity coefficient, and there's no way you can't predict this from first principles. You know which things are going to mix not going to mix well because they're different in size or different in charge. but the only way you can really constrain those is to do experiments or make calorimetric measurements, because you have some excess free energy there which you can measure with a calorimeter. But fortunately, a lot of effort has been expended on this, and we have data for many of the minerals that we're interested in. Okay, so I wanted to expand the standard states, and what I'd like to do now is to talk about another kind of standard state, another kind of mixing, which is aqueous solutions. Okay, so aqueous solutions are really important in our sciences, and we're going to talk about their properties, but in order to do that, we're going to introduce a different kind of standard state. And the idea is as follows. Let's suppose you're cooking something, you're making spaghetti, let's say. What do? Well, you boil a pan of water and you put salt in. Usually you put salt in. And we ask ourselves, what happens as we put that salt in? Well, we know that the sodium and the chloride in the salt, well, first of all, we know that the salt is sodium chloride, but we know that the sodium and chloride in the salt dissociate from one another as we dissolve the salt in water. And so what happens is, in the structure, we know it's a face-centered cube, the crystal structure, and we got smaller sodiums and bigger chlorines. And they alternate like so. And each sodium is surrounded by 6 chlorines and vice versa. Okay, face-centered cube, like so. So now what happens is, when we put them into water, we actually separate. If we put this sodium chloride into water, we separate the chlorides, which of course are nominally negatively charged, and the sodiums. They separate from one another. And let's suppose we could measure the chemical potential of NaCl. Which way am I going to do this? Yes. Plot the chemical potential of NaCl against RT ln concentration of NaCl. Okay, so obviously this is going to be negative, except we'll get to, when that's 1, it should in principle be 0. Okay, and let's suppose that that's the free energy of pure NaCl. And what happens is, as at infinite dilution, this is infinitely negative, right? So sodium chloride is infinitely negative in concentration, and so its chemical potential is infinitely negative. But very quickly, of course, it starts to have a finite concentration as soon as you put an atom in, and we find that there's a region. Oops, that's meant to be a straight line. That the chemical potential increases as the concentration increases. And in a linear fashion, this sodium and chlorides are separating, but we have a linear increase, and then it starts to go rather non-linear, and the free energy goes up till we get there. And at that point, the chemical potential of NaCl in water is the same as the free energy of pure NaCl. What happens? Well, it no longer dissolves, right? You reach saturation. That's what will happen if you're pouring your salt into your water, not thinking about it. Eventually, it will saturate. So that's the saturation. Now, obviously, the ions here in solution are dissociated from one another. We've broken down the crystal structure. So the interactions between the ions, sodium and so on, and chlorine, are completely different from what they are in the structure of pure NaCl. So to some extent, it seems rather strange or crazy to use pure NaCl at the pressure and temperature of interest as our reference or standard state. But we don't do that. What we do is we take advantage of this linear region in which chemical potential is a linear function of concentration, and we extrapolate it to 1. And we say, let that be mu 0. Okay? And that's what we do for ions in solution. We take advantage of this linear region, extrapolate to concentration 1, and that extrapolated point, which actually we can determine, is our reference or standard state value. So mu 0, it refers to a solute standard state. And in solution, the sodium ions are surrounded by water molecules. Our water molecule is bent like so, and the oxygens have lone pairs of electrons, so it has a little effective negative charge, and the oxygens, the water molecules surround the sodium and pointing their electrons at the sodium. That's what they do at low temperatures. At high temperatures, they're spinning around, so they don't do that. But at low temperatures, they point their oxygens, and they're attracted. Obviously, the oxygens which the electrons which have a negative charge on the oxygens, that negative charge points itself at the sodiums. And the cages in between, this is where the chlorines sit. Okay, so the sodium and the chloride are completely separated from one another by these water molecules. And as I said, completely different environment. This attraction between the electrons, the lone pairs of electrons on the oxygen and the sodium ion is sufficiently large that it can actually reduce the volume of the solution. Okay, so let's all right, so using our standard state, our infinite dilution standard state, we can actually get the chemical potentials of the individual ions. Right? Mu Na plus will equal mu 0 Na plus RT ln concentration of Na plus. Okay, so this is the concentration. all the while taking advantage of this extrapolated standard state. Okay, so in theory, when Na plus is 1, whatever that is, I'll tell you in a moment, we're in our standard state. Okay? Now, this is the concentration. Now, you're probably used to the idea of molar concentration, which is the concentration in terms of moles per litre of solution. So molar is moles per litre. That's not so useful for us in geology because we're interested in some cases, quite high temperature solutions. So coming out of black smokers, for example, on the seafloor might be 200-300 degrees. And so if we're interested in those sorts of phenomena, as we raise the temperature, of course, the volume goes up. Okay, so what will happen is if we have a 1 molar concentration of sodium at 1 mole per litre, as the volume of the water increases, as we heat it, it expands, and that amount of sodium might be in 2 or 3 litres of water. So this concentration unit is temperature dependent, which is basically a pain. You don't want to have your concentrations to be temperature dependent. So what we do is we define the concentration as molal, which is moles of sodium per 1,000 per kilogram of water. Obviously, a kilogram doesn't change its mass with temperature, unless it's going at the speed of light, of course. But anyway, but that's a different matter. So we use molal, and our standard state is defined as a hypothetical, because it doesn't exist, one molal solution infinitely dilute in water. I know it's kind of funny, but there you go. So we're using this really, really, very, very, very high dilution region to define our standard state. All right, I think I'll stop there.